Elena Flokas from the University of Athens and myself, Chaim Kotiel from the University of Haifa, we will co-chair together this session. And this will be an international session with participants from several countries. We have one invited paper and 6 other papers. And each of the papers will have 15 minutes, 12 minutes of presentation, and 3 minutes for question or discussion. And the invited paper will have half an hour, again 25 minutes of presentation, 5 minutes for discussion. And our first presentation will be by Dr. Marion Schroeder from Germany, from DLR, and I will ask Andreas to introduce Marion.
Good afternoon. On behalf of the organizing committee, I'm honored to prologue our first invited speaker, Dr. Marion Schroeder-Homscheid, from the German Aerospace Center, DLR. Dr. Schroeder took her diploma in meteorology from the University of Karlsruhe, and since 1998 she's a staff scientist at the Atmosphere Department of the DLR German Remote Sensing Data Center, DFD. Her research interests include applications in energy meteorology, since it's responsible for the MSG value-added development at DFD about solar radiance, clouds, water vapor, and snow. Also, in her research institute is included the aerosol retrieval development for ERS-2, Envisat, and MODIS, and the assimilation of aerosol satellite measurements into air quality models, and finally, aerosol modeling. Concerning her research activities recently, she is the project manager of the Envy Solar project, and also project manager for a project dealing with solar energy production forecast system for Spain. Both are projects of ESA, the European Space Agency. Also, her research activities are related with the ESA Space for Energy project dealing with the grid integration of solar energy, the EU project Energeo, the EU Coordination Action Measure on Solar Resources, and the EU project Heliosat 3 on improved retrieval of solar radiance at the surface. She's also involved in project GEOS and MAC. Well, personally speaking, I didn't have the chance to meet Marion before, but we tried to convince her to come at our conference, and she kindly accepted. And the reason was that 3 years ago, the first conference in energy meteorology was organized in Germany, and from that time, everybody was very excited in Germany, and I was keep listening for every German colleague that it was a great conference showing all this new field of meteorology and its future aspects. So, Mario was the local organizer of that conference, and that's the reason that she's here now. So, Mario, it's a privilege to follow your talk about applications in meteorology.
We will notify all the speakers 2 minutes before their time exhausted.
So, thank you very much. Thank you very much, Andreas, for the introduction. Well, welcome for this afternoon session. And, well, I'm pleased to tell you a bit about the upcoming field of energy meteorology. So I will take my extra time compared to the other speakers to discuss a bit what are the fields or what are the applications we deal with in energy meteorology. And afterwards I would like to switch to my own work, which is mainly dealing with solar energy, but I had a special request to extend the range of the talk a bit towards the general applications. Well, for the solar energy part, for my own work, I would like to report on the solar irradiance databases, on the long-term databases, where especially the improvement with aerosol information is the most recent and most urgent task. and talk a bit about grid integration. If I'm talking about the grid, I mean not the IT grid, but the electricity grid, and there any kind of nowcasting and forecasting approaches we will probably need. Well, what is energy meteorology? I have to give credits to a colleague of mine, Mr. Detlef Heinemann from University of Oldenburg, who actually, at least to my knowledge, raised this term, saying there is a need to combine the energy community, the electrical engineers, the physics people, with the meteorological community, to combine the approaches, as the meteorologists don't really answer the needs of the electrical engineering people in terms of grid integration and power supply, while also the engineers don't really have a feeling for the atmosphere and what's going on there. So that's the need for this new field of energy meteorology, and generally we can say the impact of all kind of atmospheric phenomena on energy supply is a task, and that deals both with conventional, where we have a certain historic record, and also with renewable energies. I would like to go slide by slide on the different fields of energy supply and try to give you an impression what people are working on. Well, major topic in terms of solar and wind energy is the question: we will have larger shares of the renewable energy sources in our energy supply system. So those sources are fluctuating sources which we cannot switch on and off like a conventional power plant. So we have to adapt with these natural fluctuations. So the engineers have to think about meteorological boundary conditions much more than before. And also, if you simulate the electricity flow within the grid, you get a dependence on meteorological patterns, which at least on the production side have not been before, only on the demand side. The site selection for power plants is one of the fields we have most experience. This process takes some years, so that's exactly the time period we use it, the meteorological information for the site selection purpose. And once we have power plants, the monitoring of their performance, the actual performance compared to the performance we would estimate as a meteorologist for a solar or wind power plant, is an upcoming task. Well, for bioenergy, up to now the bioenergy community uses typically average value for a country or a larger region, but having that in a spatial resolution and also with temporal variability is a new step which is gamma at the moment, using soil vegetation atmosphere transfer modeling, so vegetation modeling. The classical parameter is the net primary productivity, and some time ago we started to think about, well, carbon content created in vegetation. Why not calling that part which we would like to use for energy use heating value or energy content, and combining these two communities here with a bioenergy model which certainly takes account any concurrent usage and any food production wishes and all that. But then you can switch from coming from atmosphere and soil information towards a better modeling of the bioenergy resource in terms of biomass. Another field which I personally expect to be a very important field in, let's say, next 10 years is the facility management, especially if we have energy efficient buildings. I mean, at the moment, I think in most European countries, we think about we should make our buildings more energy efficient, we should change our construction methodologies. But once we have such energy efficient buildings, we have to be aware that the thermal inertia of all these buildings will be much higher, and we need heating or cooling control mechanisms. And these are dependent on temperature, on irradiance, on cloud cover. And what we see at the moment is that the air temperature at night time, and also the issue of do we have any fog or do we have any delayed solar warming, is not really taken into account by any heating or cooling system. Typically we have just small measurement devices, but those measurement devices or the control system does not know what's coming up in the next few hours. So we typically have an over control, we have an overheating or overcooling on the other side, well, for my case in Germany, it's more overheating, I have to admit. But anyhow, people tend to react quickly and open the window or switch the cooling to a higher level. So that immediately creates additional energy use, which would not be necessary if the system would have known that in advance. So any kind of building control driven by meteorological forecasting information is certainly an issue. What we from the meteorological community have to solve for that, especially nighttime temperature prediction, was not in the focus up to now, and at least in winter, at least in Germany, I can tell you that can be completely wrong, 5, 6, 7, 8, or even above degrees, and then, well, this market which is behind is very, very critical. I mean, if you feel uncomfortable in your home with a new heating system for more than 3 days, you throw it away, you tell everyone it's bad, you should not buy it, you should not use it. So you have to put it high reliability. So any case in nighttime temperature prediction error of that size is highly critical for that application. In terms of fossil fuels, the field, well, it wasn't used, no one used to call it energy meteorology, but all the fields of trading, commodity trading especially, is using meteorological information for quite a long while. And what also has been established, I think, in the last 5 years in most of the large electricity grid operators, is that they calculate the electricity demand, so what they call the load, as a function of either irradiance, in, let's say, German-speaking countries, or French-speaking countries. It's typically modeled with cloud cover. As well, generally in the electricity grid, you always have to permanently balance all kind of production and consumption. As I said before, renewable energies will bring in a non-controllable production side, but also the consumption side always had this dependence on irradiance conditions, so especially daylighting, but also all kind of heating systems show dependence. Also gas supply or gas consumption shows dependence on irradiances. So that is already well known and operative, but I think it's also part of that what we nowadays call energy meteorology. Well, something which is I would also count as part of it is the adaptation to climate change with respect to the energy supply system. So on the one hand, it's the increased cooling, which is expected as a new load part. Combined with hydrology, the water supply issue for the thermal power plants, having in mind both oil, or coal and nuclear power plants, so mainly the water is taken from rivers, so if we have the water levels is not sufficiently high, the cooling water availability is not guaranteed anymore. We had several shutdowns of major power plants in the last few years. Also, at least what in Germany is a main issue, the coal towards the power plants is transported on the line, so we get into trouble with water levels, so the coal transport way is not guaranteed on that way anymore. And of course, well known here in that community, storms, floods, any kind of extreme events increase the vulnerability of our energy supply. So I think that makes up a wide range of the applications we can have in that field. And well, I'm happy to be here to discuss some of these items with colleagues here from the atmospheric science community. I have to say personally, I have been in contact with colleagues from the renewable energy community here in Greece, and I'm now happy that this opportunity is there to get the contacts to the atmosphere. Well, now I would like to turn from this general introductory approach towards the recent DLR project. And here, I focus on solar power. I had some experience with the building issue, but as the solar power is such a boosting market, I completely focus at the moment on the solar power. So, also a word on the background of DLR. Well, you may be aware that if talking about solar power, You can talk about photovoltaic systems on your rooftop. You can talk about larger 1 megawatt areas of many, many photovoltaic modules. You could also talk about tracking photovoltaic systems where the panel follows the sun, or you could talk about concentrating solar power. And I put you one image here in the middle. This kind of technology where you have this solar, the mirror, the truss, which concentrates the energy towards this heat transfer fluid tube. Well, it mainly generates heat, which later on is transferred towards steam, and a classical turbine is used, like in a gas power plant. So this kind of technology, or you can imagine a solar tower where you have lots of mirrors concentrating towards the receiver on the tower. This kind of technology has been developed by DLR, other institutes inside DLR for quite a long while. And those people in the system analysis branch, in the energy research program, worked for potential studies. And I gave you here the most known studies, which are called MET-CSP, Trans-CSP, and Aqua-CSP. So CSP is concentrating solar power. So one study was dealing with the potentials around the Mediterranean. One was discussing about, well, how could we get electricity produced in Northern Africa from Europe? So what about transmission lines, electricity grid, what kind of grid would we need? And is the potential available? And the third study was dealing with seawater desalination and therefore drinking water plant in Northern Africa, using that technology instead of a diesel generator. So for these kind of studies, they came up with, well, can you provide us a map of the radiance of that area? So what kind of solar potentials do we have? And they came to us in the space branch of DLR, so people dealing with atmospheric science, and remote sensing activities, and we actually, this kind of map was derived from Meteosat satellites. You may know these three acronyms: the Desert Tech Industrial Initiative, which is now heading towards such kind of power plants around the Mediterranean. The European Commission is including that into the solar plan, or much of that work is done with the Trans-Mediterranean Renewable Energy Corporation. So that is the framework of my work, how I went into that field, trying to answer these requests. If you dig a bit deeper into the energy supply system, you find quite a large number of requirements. We have this standard way of saying, well, the planning phase here, where you need long-term time series, and then once a power plant is existing, you go to what the plant management area, where you need near real time for performance monitoring or the forecast. On the one hand, you have the plant management optimized, the load forecast, that's what I explained a few slides earlier, to integrate the solar or wind power, whatever, or the renewables. So issue of grid stability and issue of energy trading. So that is the field where we can work with forecast. But on the other side, with the long-term time series, the first ever asking it is the political part. They are asking from what kind of potentials do you have in an area? Does it make sense to have any kind of subsidy program in our area? What are the resources which we actually have, and where are they? Should we have any kind of specific areas reserved for that? All such kind of questions are raised by the politicians. While once the engineers start to work on that, they would like to develop certain power plants, certain location. Then we deal with the site selection with typical conditions at a certain point. Or what is also very important, we always in the engineering part you have several pieces which you can adapt to the local conditions. So knowing about the local conditions, spatial and temporal variability, the frequency distribution of values, and that's all the same if you talk about wind or solar, that's all the same. You have plenty of opportunities to use it in the planning stage. And well, of course, that is the background for any kind of investment decision. And well, transferring that towards meteorology, we talk about climate, weather, and forecasting. So it's our traditional field. The point is we have to learn what is behind these requirements in these user fields, and we have to learn to talk to the engineers responsible for building power plants or setting up electricity grids. So if we look into the solar irradiance databases, we set up a so-called Solemi database, which is based on Meteorology satellite information. So going back to the 80s, or in the archives, it's available for fast access since '91. You see the area of the Meteosat Prime satellite, but also we focus at DLR towards the Asian areas as well, and look into the east, Meteosat East. I would like to mention that at the moment we are focusing mainly on direct irradiance. As I said before, we're using concentrated solar power. That means direct irradiance is concentrated somehow and used afterwards. If we think about photovoltaics, then we need global irradiance. That's, well, for us it's a bit the byproduct. If we get direct irradiance, then we also get better global irradiance. But that's, well, a major difference between the technologies, and well, my talk will be more about direct irradiance. So what is the current status of irradiance from satellite? So what can we expect? That's a typical image of this cloud index, as we call it. And from cloud index you derive the global, or later also the direct irradiance. So what is the typical accuracy you can get at the moment? You have to distinguish between hourly values, daily sums or monthly sums, and well, of course you see an increase of accuracy here with the average accuracy, but that isn't the interesting number here. Global irradiance, the accuracy is up to 15%, and well, if we ask, well, why only 15%? I mean, investment decision would like to have 2%, 1%, 3%, 15%. They always say, oops, we can't use that kind of data. But then we typically show up that slide. It's the root mean square difference between two measurement locations as relative percentage value over the distance between the sites. So that was made for Swiss irradiance measurement stations in Brazil and two networks in the US. So you get this typical curve. Some people will call it a variogram, others will say, oh, I know that standard graph intriguing approaches. And what you can do is, on the one hand, look at the y-axis. So you see from that the theoretical lower limit, which we expect from good ground measurement, is around this 15%. So if we compare that to the value we have, if we compare against point measurements, we claim that we can quantify this point area error by that, and say we are close to what is possible if we compare against point measurements. So the missing gap here is still the geosite parameters, the water content and aerosols, but here we are close to what we want. The other information here is, I mean, you could say I just take the next meteor station if I want to develop a power plant. And actually it's not a good advice as soon as if you are away 20, 30, 40 kilometers from your ground measurement station. Even if it's a perfect station, you will be, the error will be higher than if you take the satellite, which has lower accuracy, of course, than a ground measurement station, but the spatial representativeness is rather low for irradiance. For direct irradiances, oh, I'm sorry, you cannot really fully see that. Can you see a green curve here, which has a peak here, and the red curve, which does not fit that peak here, and it gives higher values here? That's frequency distribution of direct irradiance. So yeah, can I see any nodding? Did you see that? Okay. This peak makes us a trouble. I mean, in mean direct irradiance values, we are, well, it's quite acceptable what we can reach, but what we completely miss at the moment in the standard databases is this overestimation of the high values, or we don't miss it, we have it, an underestimation of the medium values. And if you create a larger power plant of that concentrating solar power, a large, let's say 2 square kilometer area power plant, and you optimize all engineering devices to the wrong frequency distribution, then you end up with an error which is really, really high. I cannot say you a number, but I would expect it's 20–30% can easily be reached in the power production. So we know that this mainly comes from the missing influence of aerosols, which at the moment these irradiance databases are built always, well, you take clouds into account and you have to assume what is the clear sky atmosphere at that time. And at the moment, people are using, I mean, coming not from the atmosphere field, but coming from the engineering field, they're using climatologies. So, well-known one, the Global Aerosol Climatology Project one, or the AeroCom, or well, we also have one available from the NCAR match model. So that is just annual optic mean, and you already see the major differences of the climatologies. And then please imagine they are calculating, or you have to calculate hourly values out of a July value. We don't distinguish at the moment between the July of 2000 from the July of 2001. And we don't distinguish any specific hour or day, we don't get any events. That is the status of the art used at the moment. And then, of course, it's not really surprising that if you are aware of aerosol retrievals from satellite, of aerosol modeling, coming from the health community, that you get the idea, well, let's use chemical transport modeling. So what we, at the moment, doing is we apply the NCAR match model, which is a global aerosol chemical transport model, driven with NCAR reanalysis fields. And we use this model to simulate a large reanalysis back to the 80s in hourly resolution, which then here just a snapshot. That's a case from MSG where you see a dust outbreak situation which then moves over Spain, and well, just qualitatively you see that event also in match. If you do it a bit more quantitatively, you start on the right hand side. That is AOD compared versus Aeronet for the whole year of 2004, and you see a large amount of stations, which is in Europe, Africa, and the Middle East, which at the moment is in our focus. And what I put in here is simply the correlation coefficient. So blue is the new data set, match, which really has an hourly resolution, and red is the one value per July or one value per August. So even if, not the question if the match model is the optimal model for hourly or daily aerosol modeling, but just compared to a climatology, you of course have a vast amount forward here. Or if you look on the irradiance, now you can see much better this peak we had before in the direct normal irradiance versus the, is that the 25-minute sign? I'm sorry, I thought I started Q2, but okay, well, I can go ahead. Well, but it's not really a problem. So we see a major improvement here. Okay, well, just to announce, all that work will be included within MAC, the GMS Atmosphere Service. So, I would like to make you aware of the two grid integration issues we have. We have 2 points of view. One is the transmission system operator point of view, which mainly deals with grid stabilization, 1 to 2 hour forecasting, and we have the power plant operation point of view, which deals with, well, getting an access license for the grid at the beginning, then the plant operation, and that's the main issue at the moment, the market participation, where you have to predict your production for the day ahead and the intraday market sessions. So, then I finally would like to show here this case of Heathnoth, which is a collaboration with our Greek partners of Press, where we have here a network with separated photovoltaic systems. and well, some wind energy, some diesel generators. And so what happens if we have a cloud system which moves over the island, which is located here? What happens if you talk about electricity is you have a voltage drop. If one system by the other is shadowed now, and if you look more detail, it's already a percentage voltage drop. And if that gets too large, you get problems in terms of outage risk. So that is a study here, having the voltage over time from 1 minute measurement of the radiance at the ground compared to satellite input at 30 minutes. You see here that's direct irradiance, which then is shadowed close to the. So mainly the method is the two curves are rather similar. So we have the chance to use satellite irradiance information to monitor the status of the electricity grid like heat node. And while the outcome is more or less this 15 minutes or 30 minutes advance notice we get from the Meteosat satellite would be adequate to monitor the status of the system continuously. Or another application you can do if you have lots of larger photovoltaic systems, and that's what I expect also for your country as the next step, that you have a forecast, which is called the schedule here, the production forecast for a certain day, and then you see the actual production and you see these gaps. And these are the critical gap we cannot expect a lower or also higher production. And that's the focus here for short-term forecasting. So these are the issues if you are responsible for keeping the grid stable. If you are responsible for doing the production, you think more about power plants, like you see them here. And then you have to provide forecasts at the day before for the following day, but you have chances to update during the day for the rest and to correct your forecast. And that's different. Normally we have one forecast per day, and with 6 hours or 12 hours later we get another one. Here we have the chance to update. And that's only the requirement here from the Spanish market, but I expect that to be also in other areas. I skipped that one. I skipped that one. Summarizing, at the moment we have only global irradiance forecast, so the whole field of direct irradiance forecast is not available, especially also hourly resolution is this. So what can we do at the end? We suggest an approach to combine the deterministic forecast with model output statistics for this day-ahead forecasting, and then during the nighttime take the satellite information in the classical nowcasting approach, and finally during the day again take the short-term forecasting in terms of cloud movement vectors, like you see here. But the question is, what is the accuracy we can gain? So can we do a day-ahead forecast with cloud motion vectors? Certainly not. But what is the expected time range we can have? So we say up to 3 hours. That's the case for German and for global irradiance. I expect it's worse for direct irradiance. So that's persistence versus ECWF forecast, and that's if you take these cloud motion vectors into account. And what I think is also pretty important is that you be able to classify the situation of the cloudiness. So what we do here is fractal box dimension versus number of cloud elements, and then you find, that's a station in Spain, you find certain differences where you find scattered clouds, broken clouds, overcast, or isolated clouds, and that's the basis of an indicator development for the type of cloud field and the type of gaps expected in terms of energy production. Okay, so I try to give you in flavor of what energy meteorologists talk about, and what I hope also you will talk to me about your experience later during the day, the different fields of wind, solar, bioenergy, buildings, energy demand, adaptation strategies, and fossil generation, and I try to give you a bit of flavor of what we are doing in terms of nowcasting and forecasting. May I have one announcement? Those for you attending the European Meteorological Society conference, there will be a session on energy meteorology with much more in detailed information about that. And those who would like to work a bit closer in that field, there is an upcoming cost action of short-term high-resolution wind and solar energy production forecasts. So on behalf of the Heimo from the company Meteorology in Switzerland, I would like to invite everyone who is interested in such kind of cost action to participate. Thank you very much. Thank you very much.
Thank you very much for your very interesting presentation. We have time for one or two short questions. Well, if there are no question, I would like to ask, are there places or zones in the world that this methodology cannot be applicable?
You mean in the sense where we don't have information?
For example,
not accurate enough?
Both.
Okay. Well, if we deal with geostationary satellites, we have luckily a certain coincidence of the solar belt and the location of the satellite. So if you go, let's say, further than 6 degrees north, so Scandinavia, UK, which has certainly the potential for photovoltaic systems quite a lot, there we would need to get other data sets, well, polar orbiting satellites. There we have the at the moment. In terms of accuracy, I mean, the aerosol issue I pointed out several times, the Middle East, everywhere we have larger dust outbreak situations are, well, at the current point of research to prove that, as that is a major reason also for solar.
Okay, thank you very much.
Next presentation is entitled Patterns of Wintertime Jet Stream Variability by Dr. Athanasiadis and Professor Wallace. It will be given by Dr. Athanasiadis.
I'm glad to be presenting in this particular session, and let's see where we start. Okay, so I'm going to present some results from some previous work I did with Professor Mike Wallace in the University of Washington in Seattle, where I spent a couple of years as a postdoc there. And this is going to be on jet stream variability patterns in the winter and their relation to storm track variability, and some some of the known extratropical teleconnections. So let me mention that an article that we have submitted on this work is just got released in the Journal of Climate for the ones who are more interested to see more. So to give a short introduction, for the ones who are not that involved with teleconnections, these are basically large-scale climate variability patterns that have been traditionally defined using anomalies of surface pressure or mid-troposphere geopotential height anomalies, either using correlation analysis or / teleconnectivity approach, or with empirical orthogonal functions and principal components. So in this study, we try to explore an alternative approach and define these patterns using the upper troposphere zonal wind, the jet stream variability, and to see what are the benefits in this approach, and to relate these jet stream variability patterns to the storm tracks, because the variability in the storm tracks goes hand in hand with the jet stream variability. So here are some statistics from the zonal wind field at 250 hectopascals, and we have used unfiltered daily fields data for this, just to show the robustness of the patterns that we derived. Although you get very similar results if you use monthly mean data as the usual approach. And these are for December to March, in the period December to March. So I'm showing you here first on the left the climatological mean of this field, where we see two zonally elongated jet streams slightly spiraling towards the pole. And you can see, for example, that in the western North Pacific and the North Atlantic, there are two separate jets, at least in the climatological mean. And this is what we call the subtropical jet, and this is the eddy-driven jet. But at particular times, this is not necessarily the case, but that's the climatological mean. So this black, this thick line shows the core of the jet, and we have used this in the plots just to see the relation of the patterns with the position of the jet. So in the middle we see the variance of the same field, and the variance is larger here in the North Atlantic and the central North Pacific, while we see that although the jet is very strong in the Eurasian sector, the variability is very weak there. So we have focused our this study in the Atlantic sector and the Pacific sector. And on the right we see the teleconnectivity field for the zonal wind, and basically teleconnectivity for a given point gives you the strongest anti-correlation between the temporal correlation, anti-correlation between this point and a time series at any other point. So here we see a tripole, two distinct and independent tripole patterns. So if you think the traditional picture of the NAO being a dipole in the geopotential height, in terms of zonal wind anomalies, you expect an anomaly in between the dipole and an anomaly at the poleward side and another one at the equatorward side. That's why we see tripole patterns here, which are very well tied on the position of the jet itself. So for these sectors, first for the Atlantic sector, we have applied EOF analysis for the zonal wind field. And we get these tripole patterns again very nicely there. And for example, the first Atlantic pattern corresponds to the NAO, has a very strong correlation with the NAO, while the second pattern is linked to the Eastern Atlantic pattern. And in the middle and right columns we have composites on the principal component time series of these patterns. So basically this shows us what's the picture in the positive phase of this variability pattern, and this is the negative phase of this pattern. So we see here that in the positive phase we have a distinct separated jets. So the eddy-driven jet is separate from the subtropical jet, while in the negative phase they are merged into one jet. And this has strong implications for how many storms you have and where the storms move, as we will see later. And this is for the second Atlantic pattern. For example, we see that there is in the positive phase a very weak zonally wind, zonally flow, which is an indication of frequent blocking events, etc. I will say less about the Pacific here, but basically the first Pacific pattern is basically the Pacific North American pattern from a different viewpoint. And the second Pacific pattern is a pattern that has not been seen before and has strong impacts, especially at the west coast of North America. So now we take a look at the autocorrelation function for the principal component time series of these patterns. And although we are using unfiltered daily data, we see that the e-folding decorrelation times of these patterns are longer than the traditional definition, for example, for the NAO. So here it's something like 10, 12 and a half days. That is telling us that these patterns are slow evolving, they evolve slowly, and they are very robust in this definition. To see what is the variability of the storm track, what is the storm track doing in relation to this jet stream variability, we have, I'm showing you here the regressions of a measure of baroclinic wave activity, which is basically, we have taken the V prime, V meaning being the meridional component of the wind, and prime is just the high pass filter in the high frequency component, which shows us the baroclinic wave activity. And for the second Atlantic pattern, for example, we see that this is a meridional migration of the storm track, if you like, while for the first Atlantic pattern, it's more of a pulsing of the storm track, so it gets weaker or stronger. And similarly for the Atlantic, for the Pacific, I'm sorry. Similarly, these are the regressions of precipitation into the same principal component time series. And we see how the first Atlantic pattern affects here the Mediterranean area, while the second Pacific pattern, for example, has some strong anomalies along the coast, as I mentioned before. And here is the positive phase for this pattern and the negative phase. So we see here more rain goes to northern California and Oregon there. And in the negative phase, the storms move farther north and they hit British Columbia and Washington. And an alternative way for defining these same patterns basically is instead of doing conventional EOF analysis, you can look into the paired, the coupled variability between the zonal wind field and this baroclinic wave activity field. So we do maximum covariance analysis, looking for the patterns that maximize the respective covariance. So this is the first pattern that we get, and we do this hemispherically here, not by sector, so we don't have any limitation about this. We don't impose the sectors, but it ends out that the patterns that we yield is the very same ones that we saw previously with the EOFs by sector. So this is the first Atlantic, and that's the second Atlantic, and this is the first Pacific pattern and the second Pacific pattern. So just to make some remarks from this work, we see that using zonal wind yields patterns that are very robust. First of all, with respect to frequencies included in the data, so regardless of whether you have daily means or you get monthly means or low pass filtered data time series, you get the very same patterns, and they are also independent of the particular choice of sectors. They don't depend so much on this either. So these patterns also have strong and clear climatic impacts, which are not any different to the known climatic impacts of their traditionally defined counterparts. For example, the first Atlantic with the NAO. And more importantly, they relate very transparently to the position of the jets. So there is a better interpretation. It's a nicer way of seeing a teleconnection instead of a seesaw, as they call it in surface pressures. Here you have a definition at jet level where the dynamics basically happen. Since some researchers have looked in how the storm tracks, the storms, the eddies on the jet enhance the jet, and this is a coupled variability. So we just look at this in particular. And also, we show that these patterns have a longer persistence if you define them the way we do with the zonal wind. And they also express high variances, strong proportions. And I didn't talk about skewness here, but the NAO shows a strong skewness, which has been linked to the blocking that happens in this area. And if you define NAO using the zonal wind, as we do here, you see that the skewness is even higher. And this is just 0.3 for unfiltered daily data. So to conclude, we also see that the teleconnectivity using zonal wind is stronger than if you look into the teleconnectivity of the geopotential height at 500. And we just show this as an alternative definition. And thank you very much.
Thank you for your very interesting presentation. Is there any question, please? Yes.
Is there any reason that this way of defining the variability is preferable to a more traditional measure?
Preferable?
You seem to imply
I mentioned some of the reasons. For example, you get stronger metrics like skewness, explained variance, persistence, robustness in terms of data, of frequencies in the data. So it seems that it's a more robust way from one hand, and on the other hand, it just links better with the climatological picture. Like you have the jet, and you see that the pattern just straddles the jet, and it's very, from a physical point of view, from a dynamical point of view.
It's more intuitive. I just wonder why it wasn't done earlier.
What?
I just wonder why it was not done earlier. Like the more traditional way.
Well, no,
like
people have looked into zonal wind variability, but they have looked into zonally averaged zonal wind. So there is this zonal index and many other studies, but in a more zonally averaged way.
Okay. Any other? Thank you.
Okay, we will proceed, and our next speaker is Prodomos Zanis from the University of Caracostas. His presentation with some of his colleagues will be on a regional climate modeling study for the direct effect of anthropogenic aerosols on European climate for the period 1996-2007.
Thank you very much for the introduction. Ladies and gentlemen, good afternoon. What I'm going to talk about is the sensitivity modeling study of the direct effect of aerosols on European climate. It's a study that was done at the Department of Meteorology and Climatology with our colleagues Dogras, Pitharoulis, Tegoulias, and Professor Caracostas, and also a colleague from the International Center of Theoretical Physics in Trieste, Ashraf Zakeri. It is well known that aerosols affect climate in a direct and indirect way, and in a direct way actually through the scattering and absorption of radiation, and in a indirect way through actually changes of cloud properties like the cloud albedo or the cloud lifetime. In our study, we're going mainly to speak about the direct effect, and specifically the short wave effect. Looking at these direct and indirect effects from the IPCC, what we clearly see is that mainly the direct and indirect effects have a negative radiative forcing, a negative radiative feedback on the climate, which is significant and comparable with greenhouse gases. But what is more important about the aerosols is that in a regional scale, these radiative effects can be much larger than the greenhouse effects. In our study, we used the regional climate model, which is called RegCM3, coupled with a very simplified chemical model, an aerosol model, which includes mainly 6 tracers, transports 6 tracers which interact with the model. And these tracers are the sulfur dioxide, sulfate, and there is actually the kinetical SO2 which is being emitted is being transformed to sulfate. And you have also black carbon and organic carbon in hydrophobic and hydrophilic states. I'm not going to give more details about this aerosol model. I'm going to speak about what kind of experiments we have done. Actually, we did two 12-year experiments with this RegCM3 for the recent period from 1996 to 2007. And one experiment is what we call the control run, with the chemical tracers only being transported, while the other run, which is we call from now on AF run, the aerosol feedback run, which includes the radiative aerosol feedback on the short wave radiation. So in this case, the traces interact with the model. The lateral boundary conditions were from NCEP, and the European, the domain is actually a large European domain in a resolution of 50 by 50 kilometers, going up to 50 hectopascal. And this is actually the European domain that we see that our experiments were performed. And in this graph now we see actually the radiative forcing, the mean radiative forcing for the 4 seasons, autumn, winter, spring and summer. And what I would like to mention here is actually that the largest radiative forcing you see mainly in spring and even higher in summer. If you see the maps are not shown very well as I see from here, but this radiative forcing pattern correlates well, of course, with the aerosol optical depth values. So actually you have the highest radiative forcing, the highest negative radiative forcing in the place you have the highest aerosol optical depth values. And these aerosol optical depth values are seen in Central Europe and going to the Balkans and are related to emissions of mainly sulfate aerosols, SO2. From now on, we would like to see what are the changes in meteorological parameters between the control run and the aerosol feedback run. So these are changes for, in the upper panel you see the mean temperature changes between the aerosol feedback run and the control run over the whole 12 years period for spring. And in the right you see the same for summer. What you see is actually that you have a cooling, so temperatures becoming decreasing in larger parts of Central Europe, but this maximizes mainly in the Balkan Peninsula. The changes, of course, are very, very small. So the changes are about 0.3, 0.4 degrees Celsius. So these are very small changes. But the signal that you get is somehow consistent and is located in regions which are not correlated or collocated with the places where you have the largest radiative forcing. This means that where you have the largest negative radiative forcing, you don't have the largest temperature decreases. These are not collocated. This implies that you have some synoptic, some circulation changes which can somehow explain why you have the temperature decreases in a different position from the place that you have the highest, the greatest decreases in radiative forcing. And for example, if you look at the potential height, 500 hectopascal, you see some consistent patterns of lowering, relatively lower pressures in Central Europe, Central Eastern Europe. This is again for spring and summer. And this somehow your potential height changes induce changes in the wind fields. The temperature in a place we know very well from the thermodynamic equation that can change from the adiabatic terms from, for example, horizontal and vertical heat transport, or from the diabatic term through changes in the radiation. So these changes in the equipotential height induce changes in the wind fields. For example, in the zonal winds, you see a lowering of the zonal winds in mid-latitudes, and you see also changes in meridional winds. I'm not going into the details, but what I'm trying to tell you is that the changes that we see in the temperature are mainly associated with transport of relatively cooler air from Northern Europe to the Southern Balkans. As I told you, these changes that we see in the overall period of 12 years are very tiny temperature changes. An interesting thing is that if you look at the interannual variability of the temperatures, the temperature changes are not so low. So you see difference. You see that in some years, for example, you have, as I said before, temperature decreases up to 1 degree in southeastern Europe, like in the Balkan. But there are years, for example, this is a year that we have, in 2000, that we have a decrease in the Balkan up to 1 degree of Celsius. But there are years like summer 2001 that, interestingly, we don't see decrease of temperature as an effect of aerosols, but we have even an increase of temperature in the largest part of Europe. This somehow seems like an inconsistent, but somehow implies that the way that the radiative forcing interacts with the circulation patterns of each year is different. And I'm going very briefly to speak about the 2000 case, where we have the largest decrease of temperature in the Balkan Peninsula of about, as I said, 1 degree. And that decrease was not only in the surface temperature, but also higher up, let's say, mainly located in the lower troposphere, up to 850 hectopascal. These temperature changes, was related. This is was related to a southern dislocation or a southern movement of the jet stream to lower latitudes. This is the pattern of change at 300 hectopascal of the zonal wind, and this pattern somehow indicates a southward movement of the stream. And if we try to see from the meridional cross sections, of course it's quite difficult now to explain you all the details in these graphs, but these are the changes in the meridional cross section for the longitudinal zone between 20 east to 30 east, somehow in the Balkan Peninsula over the higher latitudes. You see these temperature decreases that are really associated on one way with an increase of the downward movement from the jet stream. So you have downward movements, no, increasing of upward movements due to the southward movement of the jet stream that we see in this graph in the right panel. You have increasing upward movements. This is the vertical axis, and you have increasing of the cloudiness, which is means that you have lower temperatures in the lower stratosphere, and then you have increasing, because of the movement of the jet stream to the southward, you have a heat advection, southward heat advection of relatively cooler air, which results in relatively cooler temperatures in the Balkan Peninsula. So some key points that I would like to make, that the direct effects of anthropogenic aerosols induces small near-surface temperature differences for the overall period of 12 years, with the largest effect seen in spring and summer, when of course the radiative forcing are more negative. And the pattern of these regional aerosol-induced changes of the near-surface temperature is mainly arising through aerosol-induced changes of the atmospheric circulation, and is not specially collocated with the pattern of the aerosol-induced surface radiative forcing. A common feature in the aerosol-induced changes in atmospheric circulation for spring and summer is a small decrease of the western insolant wind in mid-latitudes. And also, another key point, the greater near-surface temperature difference is seen from year to year, as the aerosol radiative forcing interacts in a complex way with the specific atmospheric circulation patterns of each year. The effect on circulation patterns, if we make an average for the whole year, somehow becomes moderated in a long-term mean. And finally, for the specific summer of 2000, we saw a southward shift of the subtropical jet stream, which seems to play the dominant role for this decrease in near-surface temperature of the southeastern Europe. Thank you very much for your attention.
Thank you very much for your interesting presentation. Are there any questions? No questions? Everything was very clear. Thank you.
Thank you. Next presentation, snow precipitation and snow cover variability in Piedmontese Alps in the period 2000-2009. Will be given by Dr. Silvia Terzago.
Good afternoon, everybody. Snow, it is a key parameter for climate and economic system in the Alpine region. In fact, from a physical point of view, snow reflects back to the atmosphere most of the solar incoming radiation. From an hydrological point of view, water is a resource that is stored in the winter season and then released in early spring. So a variation in the amount and frequency of snow precipitation may produce a variation in radiation energy and hydrologic budget at the Earth's surface. It may influence climate over small and large scale and has socio-economical consequences on water availability for human drinking supply, for agriculture, for the production of hydroelectric power, and for winter tourism. That is one of the main income of alpine villages. Here is the presentation of the analysis of snow precipitation variability over the decade 2000-2009. It is carried out using both automatic and manual station from the ground network and the satellite imagers. Ground network gives information on fresh snow precipitation, on the snow depth, and satellite imagers gives information on snow cover extension over large scale with spatial continuity, even where at ground measurements are not available. In this study, the two information are integrated to achieve a global view on the snow precipitation variability. 10 station has been selected from the network of the Regional Agency for Environmental Protection of Piedmont, Northwest Italy. These stations are representative of Piedmontese Alps, of Western Italian Alps. 4 of them are located in the north of Piedmont, 4 of them in the southwestern Piedmont, and 2 in the central western Piedmont. They are representative of different elevation. In fact, we have 2 low elevation stations which are situated below 1,300 meters. We have middle elevation station located between 1,300 meters and 2,000 meters, and high elevation stations which are located below 2,000 meters. We use information from EOSTER and EOS Aqua satellites. They are polar satellites. Their orbit has a 99-minute period. Their elevation is 700 kilometers above the hard surface. They carry an imager, the moderate resolution imaging spectroradiometer, which perform radiometric measurements of, from the heart in 36 spectral channels with a spatial resolution of 500 meters in average, a temporal resolution of 5 minutes, and the return period over the same point on the hard surface is 1 or 2 days. Radiometric measurements performed by MODIS are processed through an algorithm which identifies snow cover through the radiometric properties of snow. This algorithm produces a daily snow cover product from the single image achieved by the sensor during the daylight, and this image can be affected by cloud obscuration. So a composite over 8 days is produced. It is the maximum snow cover over the 8-day period. Complete and homogeneous datasets are available at the American National Snow and Ice Data Center archives. EOSTERA datasets starts from 2000, while EOS Aqua dataset from 2002. For this study, EOSTERA data are used in order to have a longer time series. As the 8-day snow cover products are still affected by cloud obscuration, a composition on longer period is required to avoid or reduce unclassified pixel. Here it is presented the first results of the analysis of ground measurements. It is considered the monthly cumulated snow precipitation, and the average value in the period 2000-2009 are reported for 3 representative stations located at low, middle and high elevation, and are located in different sectors of the Piedmontese Alps. Alagna is the low elevation station. It is located in the North Piedmont. We see that the maximum monthly accumulated snow precipitation is reached in November, and this is a typical feature found in all the stations in the northern sector of Piedmontese Alps. Middle elevation station at Cegliasaletto has a maximum in snow precipitation in December, has all the southwestern station, all the other station of southwestern Piedmont, and then the high elevation station Lago Agnel has a maximum in snow precipitation in April and the secondary maximum in November, and this is typical of high elevation stations. For the middle elevation station at Celio Saretto, a longer term time series is available, and as this station is operational since 1930. The average values over the 30 years reference period 1961-2000 are considered and are compared to the last decade mean values. In the graph, in the picture, the last decade values are represented by blue bars, and we can see that in the last decade snow precipitation has been more abundant in November and December, but has been weaker in all the other months of the snow season. The maximum snow precipitation occurs earlier in December instead of January, and so there is a shift in the snowfall distribution. The seasonal snow precipitation decreased in the last decade. The average number of snowy days per month. In the lowest elevation station, the maximum is in November, in middle elevation station in December, and in high elevation station in November, with a secondary maximum in March. With respect to the 30-year reference period, the number of snowy days in Accelio is higher in December, but it is lower in January, February and March. The average number of snowy days in the whole season has decreased. For the monthly average snow depth, we can see that in the last decade, in low and middle elevation station, snow depth maximum occur in February, while in high elevation station it occurs in April. In Accelio Saretto, looking at the comparison to the reference period, we see that the average monthly snow depth has decreased from January to the end of the snow season, and the average seasonal snow depth has globally decreased in the last decade. Now we look at the temporal variability of snow precipitation, and in particular there will be the characterization of each snow season in terms of both of snow precipitation amount and snow cover extension. For the snow precipitation amount, December, January and February accumulated snow precipitation is considered in ground measurement stations, and the snow cover extension in February achieved from MODI snow cover products. The 8-day snow cover products are aggregated to generate the maximum February snow cover extension. The area on which the attention is focused is the western Alps. The maximum snow cover extension in February and its variability during the period 2000-2009 is considered. We can see that there is an absolute minimum in February 2007, when snow was present only over the mountains, and we have an absolute maximum in February 2005, when snow cover was present over the Po Valley, over the plain. A similar value in snow cover extension as in February 2005 is registered in February 2004. In this figure, the accumulated snow precipitation during winter, so December, January and February, in 3 ground stations is plotted against the snow cover extension over the Western Alps at the end of the winter, so in February. We can see that in winter 2005, when we had the maximum snow cover extension, the cumulated snow precipitation has been sparse, and it is comparable to the one registered in 2007 when snow extension reached its minimum value. The maximum cumulated snow precipitation in winter is registered in in the winter of 2009 with a considerable snow cover extension, and abundant snow cover extension and abundant snow precipitation is registered in 2004. Conclusion. In the study, we considered and we found out the main features of snow precipitation over Piedmontese Alps, analyzing the maximum and the mean value of accumulated precipitation, number of snowy days, and maximum and snow depth. For the Celios Director Station, the value registered in the last decade were compared to the 30 years reference period 1961-2000, and it is found out a shift in the snow precipitation distribution. The maximum of snow precipitation is anticipated with respect to the reference period, and a decrease in the total seasonal snow precipitation, in the number of snowy days, and in the average seasonal snow depth. Through the integration of ground measurements and satellite information, we can outline the general features of each snow season in terms of snow precipitation abundance and snow cover extension. Further investigation is necessary to recover long-term time series and have an in-depth and to have an overview of the snow precipitation characteristics in the past, and then the complete Eostera dataset will be analyzed to study the temporal and spatial variability of snow cover extension over the last decade. Thank you.
Thank you very much.
Okay.
Any question, please? In Spanish.
Is being reduced in the recent period?
Yeah.
So
in general, from our studies, it resulted that there is a general decrease at low, middle elevation station and below to 2,000 meters.
So I wonder whether is this because of the precipitation is reduced even as equivalent water, or maybe it's an effect of increased temperatures that give more rain rather than snow at the lower elevations, where it is not so much below freezing.
Sorry, excuse me.
Maybe it's I don't know whether this reduction is because you get less precipitation, even if it is just equivalent water.
Yeah.
Or it's an effect of higher temperatures.
It is probably an effect of higher temperature, and then a combination of both temperature and precipitation. Yeah.
Mm-hmm.
Any other? Okay, thank you very much.
Okay, our next speaker arrived from Canada. It's Lily Ioannidou. With her co-author Yao, she will present the influence of the Arctic Oscillation on anticyclonic development in Central and Western Asia. Please.
Okay. Good afternoon. This is my title of my talk, Influence of the Arctic Oscillation on Anticyclonic Development over Central and Western Asia. επιδράσεις της Αρκτικής Ταλάντωσης στα υψηλά βαρομετρικά συστήματα της Κεντρικής Ασίας. It is part of the work I did with Professor Peter Liao at McGill University a couple of years ago. Sorry. Okay, that's it. Okay, so I'm going to talk in the following order. I'm going to give a brief introduction on the Arctic Oscillation and on the blocking anticyclones. These are both subjects I will touch on in the presentation. Then I will talk about the data we used and the analysis method. And finally, I will present our results on the blocking anticyclones of Central Asia. I will talk about the changes we identified with changing phase of the Arctic Oscillation. And if time allows, I will talk about the relations to the blocking anticyclones of the North Atlantic and to the variability of the North Atlantic jet stream. So Thanos was an excellent introduction. A little bit about the Arctic Oscillation. What is it? Basically, it is a dipole oscillation of mass between the Arctic Basin and the surrounding zonal ring. It affects predominantly the pressure field and the wind fields. So when we are in the positive phase, the pressure over the Arctic Basin is lower than normal, and the pressure on the surrounding zonal ring is above normal. This causes the jets to intensify and to shift to the north. When we are in the negative phase, the reverse happens. So we have increase of the pressure of the Arctic Basin, and we have a lowering of the pressure in the surrounding zonal ring. This results in a weaker zonal jet, and it tends to move south. The pattern at the surface is obtained as the pattern of the leading mode when the mean sea level pressure field anomalies are submitted into NEOF analysis. And the AO index describes the variance, the amount of variance rather, that is associated with this leading mode. The lower plot shows the time series from the early 50s onwards until the 2000 years. There are two things that the time series of the AO index is informative about. First, on whether at a given point in time the oscillation is in a positive phase or a negative phase. Another thing it tells us about is the amount of variance that is associated with this mode at that point in time, whether it is large or small. Okay, a little bit now on the Asian blocks. The area that the vertical line points to, it is in northern Asia, around 50 north and around 100 degrees east. Is known for the development of blocking anticyclones. Blocking anticyclones are anticyclones with a characteristic of very long persistence. And they're also known as the Ural blocks. Now, why are we interested in the Ural blocks? Basically, it is well known that the Asian continent during the winter period is covered by the Siberian anticyclone. This is a large-scale, low-level feature. And often it happens that the blocking ridge of the Ural block couples with the surface field and produces a local amplification of the Siberian anticyclone. When this amplification happens at its western southern edge, approximately the area delineated by the red box, it implies a westward extension of the Siberian anticyclone, and it was shown that what happens there has an immediate effect on the conditions in the Balkans. Cavaggio showed that it has been associated with extreme rainfall events over the Balkan Peninsula, and Kutel et al. Showed that what happens in the Caspian region sector in particular, and the teleconnections that affect that area have implications for the temperature and rainfall over the Anatolian Plateau and the Balkans. These are classical figures. I don't want to insist too much on them. Basically, they show the horizontal structure and the vertical structure of anticyclones in general and blocking anticyclones in particular. The horizontal structure basically shows a dipole where the high pressure anomaly is situated to the north and the low pressure anomaly to the south. And then the panel at the bottom that shows the vertical structure basically conveys the information that it consists of a temperature anomaly in the middle and upper atmosphere, which in the temperature field will show as a positive temperature anomaly. In the stability field, it will show as a negative stability anomaly, and likewise in the potential vorticity field. A little bit more specific about the Asian blocks, their forcing mechanism at this point, the dominant view is that they owe their generation to Rossby wave that is of Atlantic origin and is propagating from the Atlantic over the Asian continent. The quantity MT is one of the formulations that was given to a vector called wave activity density flux vector. It has a very complex formulation given by the formula on the right hand side, but the main properties that are of interest here is that it is a conservable property following the wave propagation, and also it is aligned along the direction of wave propagation. Using this diagnostic tool, it was shown that what the Asian blocks in particular, what happens with the Asian blocks in particular is that there is absorption of wave activity at the blocking latitude as the block amplifies, and their decay starts when this wave activity starts to be re-emitted downstream. Schematically, it is shown on the left figure. The first three plots are the phase of block amplification. So we see the wave train approaching from the west and propagating downstream. At the same time, the wave activity density flux vectors are divergent and upstream. Then the last three plots show what happens after the block has reached peak amplitude and starts to weaken. Show basically that the wave activity density flux vector shifts downstream and becomes divergent. And the wave train starts to be seen downstream, but it is not so evident in these figures. And finally, a little bit on the Rossby wave train that the Asian blocks owe their generation to. This is a classical picture showing an arching Rossby wave train across the Atlantic. The path of the propagation of the Rossby wave is crucially dependent on this parameter shown in the blue box on the right. It is called the stationary Rossby wave number, and basically it says that there's a very strong dependence of the path of propagation on the flow configuration. This parameter there on the right depends very much on the speed of the flow and also on the curvature of the flow. Ray tracing technique have been applied, and they have shown that when for a poleward propagating wave, it reaches at some point a critical subpolar latitude at which this number Ks becomes equal to the wave number of the propagating wave. When this happens, there is wave refraction, and the wave is a little bit like refracted away from the pole and towards the equator. So enough on this, and now I'll talk a little bit about the data and the methodology. We use the Era 40 dataset. It's well known, 6-hourly data at 2.5 degree horizontal resolution. We constructed trajectories of anticyclonic centers using the feature tracking algorithm by Hodges. And the centers of the anticyclones were identified as maxima in the mean sea level pressure field, the geopotential height field, and also in other fields that reflect anticyclonic development like the potential vorticity field and the temperature at high levels. This is what the algorithm gives. This is an example of an ensemble of tracks obtained for the winter season of 1983-84. The crosses are the points at which the anticyclonic centers appear. The little squares show the points at which they disappear or die, if you like. And once the ensemble of tracks was obtained for the 45 years of the Era 40 dataset, Then they were projected on a grid, a regular grid that covers the northern hemisphere. To obtain the values, the estimates of anticyclonic properties on the grid points, Formula 1 is used, which basically means that at the grid point, the value obtained at the grid point is a weighted estimate of the values at the surrounding data points. Now, data points means points along the track. And the K function is basically a kernel that is a function of the distance between the grid point and the data point, and also a function of a scaling parameter, Cn, which is basically the range of influence of each data point, and it can be defined objectively by the data or by the user. Anyway, the point of all this is that eventually we get at the grid points estimates of different quantities, different measures of anticyclonic activity. What I will be presenting in the next is a quantity that we call frequency, anticyclonic frequency, and it expresses the amount of time of the winter season that anticyclonic activity is detected over a grid point and the surrounding area of 1,000 square kilometers. I will be presenting this distribution as averages for the 45 years of the dataset. It's always winter season that we have been analyzing, and then average for years of positive index that exceed value of 0.5 and also negative index of values of minus 0.5. Okay, so this is what the distribution looks like at 500 hectopascals. It covers the Asian sector and the North Atlantic sector. There are two maxima. One over the eastern North Atlantic, it corresponds to the blocks of the North Atlantic sector, and another one over the Asian sector. As you can see, it is quite extensive. It covers all the region between the Baikal and the Balkhash lakes, and the values are similar to the values of the North Atlantic maximum. The lower plot shows the same quantity, but at 250 hectopascals. There we see that the Asian maximum is a little bit weaker and a little bit further north and west than its 500 hectopascal counterpart. Now, these are the distributions of this frequency, anticyclonic frequency quantity for positive AO phase on the left and negative AO phase on the right. We see quite a bit of a difference between the two. Basically, on the left we have the North Atlantic maximum extending into Asia and forming a center at the point where you see it. And then on the right plot for the negative phase, we see that the North Atlantic activity splits in two centers, one centered over the Norwegian Sea and the other over the Eastern Atlantic. And then we have an extension from the maximum of the Norwegian Sea towards the southeast, and it forms the Asian maximum a little bit to the north and east of the Caspian Sea. Let's look at the differences between positive and negative phase. Red color denotes positive, blue color denotes negative, and basically what red color means is that we have a rise of activity there for the positive phase. Conversely, blue means that we have a rise of anticyclonic activity there for the negative phase. So in the North Atlantic, we see that it is a north to south shift. The activity moves to the north for negative phase and moves to the south over the British Isles for positive phase. Over Asia, it's quite different. The orientation of the displacement is not north-south, it is southwest to northeast. And in contrast to the North Atlantic, what we have is that the rise in pressures occurs for, the rise in anticyclonic activity rather, occurs for positive phase to the north and east, and for negative phase to the south and west, a little bit to the north of Caspian Sea. The values are not strong, but they're significant, the 95% confidence level. Now, this is a very robust pattern over Asia. You can see it in the potential vorticity field. This is potential vorticity at the tropopause level, 250 hectopascals, where it is more extensive. This is the upper plot. And in the lower plot, you can see it in the temperature field, positive temperature anomaly field distributions, and this is the lysis of this distribution. regions. So it's basically the regions where the temperature anomalies die. So it also shows in the lower stratosphere in a little bit more zonal orientation, but that is not important. What I want to emphasize now is that we tried a little bit to explain what is the explanation behind this Asian dipole, this Asian seesaw oscillation, because it is so starkly different from the one in the North Atlantic and a little bit counterintuitive, because you see the rise in pressure to the north for the positive phase, which doesn't project positively on the AO pattern. So if we look to the right, is a schematic of what the Atlantic jet looks like for the two phases of the Arctic oscillation. Top is the negative phase. As you see, the jet shifts south and becomes more zonal in orientation. And the bottom panel is the positive phase. The jet shifts north and hits Europe, is directed over Scandinavia. So what happens here is that as the jet shifts south, if I can remind you of what I mentioned about the flow parameter Ks, the geographical distribution of Ks is changing dramatically. This is what a similar experiment showed. This is model results for an experiment that was done by Nascimento and Ambrizi over the South Pacific that shows a situation that is quite similar to our negative AO situation. Basically, they have a jet, the velocity field is shown on the very left. It is jet streaks aligned at about 30 south. This causes a distribution of the Ks parameter that is shown in the middle panel. This is the meridional profile, where the peak is seen, as you see by the blue line, at 30 degrees south, and it is flanked to the south by lower values of Ks. What this leads to is a zonal wave train. You can see it on the right. I will skip what it looks like for a situation in the South Pacific that resembles the positive AO phase, but basically what happens, you can see it in the very right bottom panel, is that the Ks distribution is such that a subpolar waveguide is allowed to happen for the propagating Rossby wave train. So if we come, this is my final plot, if we come to the Asian seesaw, on the polar stereographic projection on the left, there are two potential paths for the Rossby wave that creates the Asian blocks. The one in the red is what we think happens for the positive AO phase when the jet is shifted northwards. The Ks number distribution is such that it allows refraction of the wave at the subpolar latitude, as shown by the red arrows. From there, it penetrates into Asia from the Asian Arctic coast and creates, or rather triggers, a blocking anticyclone in position P. In the case of the negative AO, a zonal waveguide is created because the Ks distribution is such that propagation is not allowed of the Rossby wave in high latitudes. So the blocking anticyclone generation position is position A, close to the Caspian Sea. And finally, the conclusions. A seesaw of the blocking activity was identified over northern Central Asia with a southwest northeast orientation. The anticyclone's position is over the Taimyr Peninsula for positive phase, close to the Caspian Sea for negative phase. There are implications for weather at the surface. The extension towards the southwest with the Siberian high for negative AO has effects on the weather of the Balkan Peninsula, whereas the Siberian high is expected to withdraw towards the northeast for positive AO. And finally, there is a possible link of this Asian seesaw blocking activity with what happens in the North Atlantic blocking, and also the variability of the North Atlantic jet stream. Thank you.
Thank you very much for your very interesting presentation. I'm sure there are questions, but unfortunately we are ahead of time. So if there are questions, you can ask her during the coffee break, and we will proceed now.
Next presentation by Elena Lukovic, Comparative Analysis of Ground-Based and Satellite Measurements over Serbia.
Okay, good afternoon to everyone. In my personal name and on behalf of a colleague of mine, Mladen Ducic, I would like to present a paper named Comparative Analysis of Ground-Based and Satellite Temperature Measurements over Serbia. Well, there is an apparent difference in surface estimated warming and those on the base of satellites and radio sondes of 0.2 degrees per decade, and these differences appear due to several reasons or interpretations. Some of three are listed here due to data quality problems, either within the surface data or radio sondes or satellite data, then due to the effects of natural internal variability or external forcings, and however, third interpretation of reason of these differences can be related to the coverage of differences in these three data sets. What was I trying to do here, and colleague of mine as well, was to analyze the two data sets, one related to satellite temperature measurements, which is a product of NASA and processed at University of Alabama in Huntsville. Those are microsound units, temperature anomalies for the area of Serbia within the given grids, Europe and planet Earth. These data sets, in contrast to Global Historical Climate Network, which also has been used here, actually has almost a global coverage, and it is available in grids 2.5 degrees of longitudes and latitudes. The layer to which this data is referred is 8 first kilometers of the troposphere. I have also mentioned that we have been used the Global Historical Climate Network for the period 79-2006. Those are surface temperature data, also available in grids, but for 5 degrees of latitude and longitude. And I must just mention that the number of meteorological stations within each grid varies actually, but using certain statistical tools, the authors of this network made possible comparison of this data. So, calculating linear trend for the planet Earth, Europe and Serbia in the investigated period have shown the values in table 1, and what we can see is that the linear trend values are higher according to surface data than those from satellite observations, and the data are the lowest, if I can say, for the planet in total than for the Europe and Serbia in all of these three cases. I must say that these differences were even higher before certain corrections that have been done at 2005, and after that period trend differences were reduced, but still is visible, as we can see here at the table 1. What also has been done here, those were moving average pentads of temperature anomalies for all these three areas, and what can be also noticed is that accordance of the coldest and the warmest pentads for the planet Earth, but not for the Europe and Serbia, where it seems that according to satellite data, coldest pentads appears 2 years earlier than for the surface, than according to the surface measurements. And what it looks like this, graphically presented. If we take just Serbia, and that was the focus of my interest basically here in this paper, and what we have tried to do is to test statistically, is there any statistical meaning in this lag of 2 years, and then we applied Pearson's correlation coefficient and got that actually for Serbia the highest correlation is with that 2 years of surface temperatures in relation to satellite temperatures. Just for this illustration, correlation coefficients with different lax times and related thresholds are given on the graph and included in the table as well. And this is the graph. If we take those mentioned 2 years, these are the moving average pentances and lines, how they look with this lag time included. What I said that was focus of my interest here was the analysis of temperature differences according to data sets for Serbia, and on annual basis, these are the differences in trends according to ANSU and data from Climate Historical Network. What I have forgotten to mention is that the correlation coefficients and results we got actually suggested that let's say a factor that was causing temperature variability over the investigated period in Serbia appeared first in the troposphere, then at the ground level, and it was suggested us to think that we should maybe give importance to external forces and factors like volcanic activity or solar activity, and I would just mention, I haven't included them here, results we got for the satellite temperature over Serbia and volcanic radiative force, where we got actually statistically significant correlations over just Balkan Peninsula, and we did it for whole Europe. And what was interesting, it was a kind of dipole with the negative values over Scandinavia and positive statistically significant values over Balkan Peninsula. However, at this step of the paper, we just have taken surface temperature anomalies from the satellite temperature anomalies, expecting that according to the reports of IPCC, temperature should be increasing more at the lower and middle troposphere than at the surface, and we got that actually we got downward trend with the temperature increasing more at the surface than in the lower and middle troposphere, with the trend line increasing over the investigated period, which is presented here, and that's 1.4 times higher than for the lower and middle troposphere. However, this paper suggested strongly inconsistency between satellites and ground surface data over the investigated period in the area of Serbia. And in the shortest, it would be all. Thanks.
Thank you for your presentation, a brief one. Any questions? There is time for... Okay, thank you very much. Last presentation, but not least, will be presented by Professor Coutiel, entitled Dryness in the Mediterranean Basin.
Okay, thank you. My co-author, Adas Reiser, should give birth at any moment, so that's why she is not present here. I would like to talk about dryness in the Mediterranean. The layout of my presentation, I will talk a little bit about dry spells and about the dry days since last rain or DDSLR versus dry spells. How we calculate the DDSLR, some examples, median and extreme values, cluster analysis and the spatial distribution, and some conclusions. Dry spells. Usually a dry period are presented by calculating dry spells, which are some consecutive dry days without any rainfall or with a very small amount of rainfall below a certain daily threshold. This use of dry spells has two major drawbacks. It is not datable, and I will explain later, and it is impossible to follow the development of a drying process. And I will give an example to illustrate these two problems. Let us assume that there is a dry episode of 42 days with a dry episode that started on January 22nd and lasted until March 4. To which months it should be attributed? Usually dry spells are presented in histograms or in month histograms. Usually it will be attributed to January, the month when it began, although the dryness was not severe and was the least. Other may attribute it to February, as all February was dry. And why not March? Although it was the shortest period in March, but in March it was the most severe because it lasted for almost 1.5 months. Okay, so we propose a different approach which is called DDSLR, and if we take the same example, the impacts of the dry period are not related to how long this dry period will continue. For example, if we, after 3 weeks on February 11, the impact of this dry period are the same regardless if the next day it will be another dry day that will continue for another 3 weeks, or it will be a rainy day. After 3 weeks, you have some impact of this dry period. So the dry days since last rain or DDSLR can, let's say, overcome these two drawbacks. It is editable, and I will explain how, and it enables us to follow the development of the dry period and to present it in a probabilistic way on a daily basis. How we calculate the DDSLR? For each day with a measurable rainfall above a certain daily threshold, and everyone for each purpose can define a different daily threshold. Usually it may be set to 0.1 millimeter or 1 millimeter, but if for several purposes it can be set also for higher threshold. So any day with a rainfall amount above this threshold will be attributed as 0. The first dry day will get the value of 1. The next one, 2, and so on, until the next rainy day, which will be attributed again 0. The values are accumulated from 1 year to the next one. And then the values are sorted in an ascending order for every calendar day. So if we have many analyzed years, so we will have for each calendar day the number of values according to the number of years we analyzed. This is a chart showing the DDSLR in Nirim. Nirim is a station in southern Israel. These values are not sorted, and each column represents a different rainy season, and each row, it's very difficult to see here the rows, but you can see the colors represent a different day. Each cell is colored according to the value of the DDSLR. The dark blue are rainy days, and the more red or more brown are DDSLR with larger values. as I said, the values are accumulated from one year to the next one, and after we sort them for every day, we obtain this chart. This is the same data as on the left panel, but after sorting. So we can see here very clearly the rainy season, which is in this. You can see the rainy season marked in dark blue. These blue are up to 1 week after a rainy day, and this is the dry period, a very typical Mediterranean climate. Now, if we look at that, it is also can be presented in a probabilistic way. We can talk about the median DDSLR, which are all the values along this line. So for each day, I remind you that each row here is a specific day. For each day, we can know what is the median value of how many days we are from the last rain. And we can also check for extreme cases. For example, we can take the 90th percentile, and of course the values here are much larger than the median values. Some examples from other stations, Lagos and Picota, both in southern Portugal. Here again you can see a very typical Mediterranean climate with a dry period, although less dry and less pronounced in Nirim in Israel, but still we can see the dry period. And two from Greece, from Syndos and from Thessaloniki, in which it is very difficult to observe the same pattern, and we can see that we have rainfall almost all year around, with maybe a little bit longer dry periods, but for only extreme cases. Now let's compare between median and extreme DDSLR. An example from Cagliari, and you can see here the distribution of the median. This value are a cross-section at the median from the previous chart, and this one is at the 90%, and you can see the differences in days between the two. And another example from Ljubljana, where the DDSLR are much lower, and the differences between the two, you can see again the median values at Ljubljana are very, very low, around 6 days. Here you can see examples of various stations. You can see very well all the stations with the Mediterranean climate, showing the very pronounced dry period, the summer dry period, which is from all 41 stations analyzed. Jerusalem had the longest one, and but still, even in these stations, we can see a very clear Mediterranean type of climate, while in other stations it is very difficult to see that, and we obtain very low DDSLR values, which are almost the same along all the year. We took these values, an example I'm doing here, an example from Ljubljana, and we correlated the daily values, the median daily values at Ljubljana with all other stations. And we plotted here all the correlations, and we can see, of course, Ljubljana with itself is perfectly correlated, but there are here some stations which are positively correlated and significantly correlated with Ljubljana. The others are negatively correlated with Ljubljana, again significant, and there are few stations here in the middle, Tortosa, Barcelona, Prilep, which are not significant. Their correlation with Ljubljana is very, very low. In the same manner, we made correlation of all stations with all other stations. Then we took this correlation matrix and we applied a cluster analysis, and you can see here the results of the cluster analysis. And basically we found two clusters, 1 and 2, and two big clusters. Cluster 1 with the majority of stations, and cluster 2 with fewer stations. But we could also divide these two main clusters into two subclusters, and they appear here according to the different colors. It may be difficult to read. I hope you can read the green one. There are Ljubljana, Verona, and Zagreb, and all the others, I hope you can read them. Now, when we map this cluster, this is more or less the map we obtain, where this line divides between cluster 1 and cluster 2, which this part are with more typical Mediterranean climate, while in cluster 2 we can see, as we have seen before, that there are rainfall all year round, and you can see here the two subclusters, 2B and 2A, and the two subclusters of region 1. Now we took all the stations belonging to each cluster, and we calculated their temporal distribution of the values, and you can see in region 1A and 1B, you can see here for median and extreme values, you can see very neatly the summer maxima in both regions, but in 1B there are lower values than in 1A, and these are the 90%, and these are the median values, and you can see the difference between the two. In a similar way, also for region B, note that the vertical scales are completely different between the two charts, and values in region B are much lower than in region A. And again, you can see here the 90% and the medians. The median values here are very, very low, around 5 or 4 days. These are regional averages. Again, when we look at these two examples, the maximum DDSLR for the median value in Cagliari are 49 days. The maximum for the 90 percentile are 180 days. So the ratio between the two is 2.19 times. So the extreme values in Cagliari are a little bit more than twice the median values. When we go to Ljubljana, the equivalent values are 6 and 36 days respectively, and the ratio between the two are 6 times longer. Here on this chart we draw all the ratios for all the stations. So if we take Jerusalem with the longest DDSLR, the maximum DDSLR, the maximum median DDSLR is 172 days, almost 6 months without rainfall. The maximum extreme value of 90% is 213, and the ratio is 1.24. So what we can see here on this chart is that despite the fact that in Jerusalem the dry periods are much longer than in Ljubljana or in other regions adjacent to Ljubljana, the ratio between extreme and median values is lower, and this formula over there gives you the ratio between the relationship between the two. So if we try to conclude, DDSLR is an innovative approach to describe dryness. It presents the probability of a dry episode on a daily basis in a probabilistic way. We can study the evolution because every day, not only the entire length of the dry period is analyzed like in dry spells, but every day got a different value. And despite the longer DDSLR in Mediterranean region, the ratio between extreme and median condition is lower as compared to regions that benefit from rainfall all year round. For example, an extreme DDSLR of 240 days in a region where the median is 170 days is less severe for most of the let's say, ecosystems which are adapted for such long periods, while if we take a place with a median of 20 days and we have an extreme case of 90 days, that will be more severe for the ecosystem to adapt because they are not used for such dry periods. And therefore, paradoxically, in the former region, extreme dry condition may be less catastrophic to the environment compared to the latter region. Thank you very much.
Thank you, Chaim, for this interesting approach. Any questions, please? Is that your last paper? The last published paper? Okay, thank you.